Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. You've probably heard of BTrees before. What are they? They too are a kind of search tree, but they are specifically designed for the case where the set of keys is so large that the search tree won't fit in your RAM. Since the cost of disk access is many orders of magnitude greater than the cost of memory access, it makes sense to optimize the data structure to keep the number of disk accesses as low as possible. The BTrees do that with a generalization of the ideas of the 2-3-4 trees. Here too we have nodes that hold a variable number of keys and a tree in which all the paths from root to leaves have exactly the same length. Deletion in this data structure is going to be non-trivial, but if we go back to what we learned with the BSTs, then we're going to crack this one as well. You'll definitely want to click the like button once I show you how it's done. Okay, so our next topic is something to do with using the same ideas in situations where you have so much data to put in your search tree that it doesn't fit in memory, and you have to put it in secondary storage. And the difference between the RAM and the mechanical hard disk is that there is a several order of magnitude difference in the access time. If you're actually talking about spinning disks, then the gap can easily be 5 orders of magnitude. 100,000 times slower to access a byte on a disk than it is to access it in memory. And so if you are spreading your tree onto secondary storage, you have to take into account the fact that operations that access a new part of the disk will have a very high cost compared to the operations that you do in memory. And if you disregard that, then the performance of your algorithm is going to be pathetic, and it may have the same asymptotic complexity, but if the factor that's hidden by the big O is something like 100,000, then you need to pay attention. So the hard disks are structured in such a way that you have these physical disks stacked on top of each other on a common spindle like this, and they all turn at the same time, and there is a kind of comb of read-write heads that access the surfaces of the platters, and this comb can move so that it spans the whole surface of the disk. And so you have these things spinning and this thing moving. And if you leave your heads in the same position, then the disk that's spinning under it, for every head, will describe a circle, and for the combination of all the heads will describe basically a cylinder of places that you can access without moving the head. And if you also move the head, then you get inner and outer cylinders. And so you want to group things in a way that you don't have to do lots of seeking around the disk to find things that are going to be accessed next to each other. So it is common to arrange things in blocks. There's going to be several blocks, block, 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 in each one of these circles, and it's easy to access the consecutive blocks, and it costs a bit more to access blocks that are in other cylinders. And so you think about all these things. It's easier to go from blocks in this one to blocks in this other one because you don't move the head than to blocks in an inner or outer cylinder. So what you do is you arrange your data into large blocks, because once you go to the trouble of reaching the block you want, then getting more data off that block is rather inexpensive in comparison to getting to that block. Because getting to that block, you have to wait for the disk to spin until it comes under your head. First, you should have positioned the head on the right cylinder. Then you wait for the right block to come under your head. Once it's there, it just spins very fast, and so you can get bits out of it. You could make it as big as the whole cylinder in the limit if you wanted, but that's not a good idea, because then you have lots of wastage if you make blocks too big. Anyway, You're going to make a similar data structure to the ones we've just seen, except that your node is going to be the size of a disk block or something big. And the trade-off is the bigger it is, the more efficient it's going to be to read stuff off the disk. But also, if it is too big, there's going to be some wastage. And if your block is not full, then reading a very big block that is not full is more wasted time for you. So you don't want to make it enormously big. But you could still make it, thousands of items in it. So the B tree is a data structure that uses this idea. It's basically the same as a 2, 3, 4 tree, except that instead of just holding up to 4 children, it can hold thousands of children. And in between 2 children, in between 2 adjacent children, there's going to be a key that separates them. So all the things on the child to the left are going to be smaller than the key, then all the things bigger than the key are going to be there, or there's going to be other bigger keys, and the structure of the block looks like this. This is a picture that I placed in your handout on page 110. So imagine a 2, 3, 4 tree as one where the blocks have t equals 2. T is the minimum number of children you can have. T is your minimum number of children. And the maximum number of children is 2t. All internal nodes have at most 2t children and at least t children, except the root. The root is excused because when you start the tree and you have nothing in it, if the root had been obliged to have at least t children, then you would not be able to start a tree from 0. So for the root, you can have 0 children. But for every other node, you have to have at least t children and at most 2 children. That's so as to keep things within a reasonable range. Otherwise, the tree would become unbalanced. So this tree is going to be balanced and is also going to be very flat. Because it has such a high branching factor, it means you can store gazillions of items with just a few levels. Because if you have even just 1,000 children with a branching factor of 1,000, then your first level has 1,000 children. Your next level has 1,000,000 children. Your next level has 1,000,000,000 children. And you see, you don't have to go down very far to reach enormous numbers of leaves, which is where you store your data. And of course, the branching factor can be higher than 1,000. So these are your keys. These are your keys. And there's space in the nodes for as many keys as are necessary to separate 2t children. So in this case, t is 64, 2t is 128, so I need 127 keys to separate the 128 possible children, which are numbered from 0 to 126, the keys. Each key has an associated payload. The payload may fit in the node, or if it's appropriate, it could be just satellite data that has a pointer in the node, and the data is stored somewhere else and it doesn't move. It's probably more common. And so this basic unit of the B tree is an internal node with keys and payloads and children. And there are also leaf nodes without keys or payloads or children, which you just have here to mark that that's the end. For each key in a node, the node also holds the associated payload or pointer to satellite data. All leaf nodes are at the same distance from the root. That's the property of the 2, 3, 4 trees. In fact, it was the BTrees that were invented first, and then they were ported back to memory as 2, 3, 4 trees by setting t equal to 2. And then out of that grew the red-black trees. This one is what we started discussing. Number of children is limited to the range between t and 2t. And a node has c children if and only if it has c minus 1 keys. So there's going to be some unused space here for keys that are not currently in use in this node, but are allowed for being in the range between t and 2t minus 1 keys. Actually, t minus 1 and 2t minus 1 keys. I make small slips and mistakes all the time. If you notice any of them in the handout, then please let me know, and I will correct. I received one last time, which I have applied to my copy and written out in the website for the course, which has a list of the mistakes I know about. So if you have a B-tree, how should you insert into a B-tree? You should be doing the same things as you have done for the 2, 3, 4 tree. This is a picture from your textbook where you have an initial tree with keys being letters of the alphabet, and you want to insert the letter B. So let's get ourselves a B. If I want to insert B, I go here, and it says this should go in here. But if I didn't insert it here, it's because I'm only allowed to insert in bottom layer. So I should go, where is it? Well, for all these keys, it should be this side, and so it's going to be in this subtree. So the B should go in this. This is at the bottom layer, so I can insert in here. It should go between B and C. But I can only do that if this is still with some spare space. Now, I can see that these small ones in here have 2 keys, so they have 3 children. So this smells like t equals 3. So if this is t equals 3, then 2t, and the maximum number of children would be 6. So the maximum number of keys would be 5. Maximum number of keys is 5. And so this means once I've done this, then this one is now full. I would not be able to insert another thing into this one. If I wanted to insert the letter Q, then Q, if I go in here, PQ would have to go in here. But this is 5, and I've just figured out that 5 is the biggest. Well, I figured that because I didn't read the rest of the stuff around the picture in the textbook, but I should have been told. I don't have to guess. If this is a B tree with t equals 3, then it's a fact. It's not something that I figure out. Anyway, it is the case that this particular node is full, and so I cannot insert the Q in this node as I did for the B. I first have to follow that procedure I described. That when I encounter a full node on my way down, I must split it. So if I split this, then its middle key, this would be this T, would have to migrate into the parent. And so T migrates in here, and I'm left with RS on one side, UV on the other side, and I can insert the Q into RS. So QRS, then the T and UV. And that's how Q has been inserted. And if I then insert the letter L into this, whoop, I meant to take this one, L, so L would go in here. But as I said, when I encounter on my way down a node that's full, and by now the root is full, I should really lock this down. Lock. By now the root is full, so when I come here, before doing anything, I must split the root. So P, the middle value of the root, goes up. All the paths increase by 1. And now I continue with my L, which is inserted into LM. It was going to go, of course, to the left of this. Has to go between the G and the M. So that was going to be in this one, and this one has space, so it gets inserted into here. And so on. How are we doing? I think there is another important thing to work on, which is I have never said, besides the initial BST, how you would delete stuff from these more complicated data structure which try to remain balanced. And that is not an easy operation. And you would be doing well if you try to work it out for yourself. But you need some tools. And one tool that you're going to use is this set of neat operations, which I want to bring to the front, and therefore I'm going to do this. Okay, so these are manipulations of the B tree in the same spirit of the rotation. So I do changes that are local and that do not violate the search tree properties, either for the things I'm touching or a fortiori for the rest of the tree. So the merge is that if I have two nodes like this that are adjacent and small enough that I could make a node that's all of them together plus another one, then I can just bring this key down over here, and J, K, M, and O makes a new node. And comes down here, and so leaves a gap between the G and the P, and that's going to be the parent of this J, K, M, and O. That's merge. Split is the opposite. If I have something like this, I could send, provided this was not full, I could send the C up there and have AB split DE. So merge and split are the reverse of each other. And redistribute is something where I'm basically pouring letters from someone into their neighbor. For example, in this case here, I have J, K, L, and O. I can pour the L through here, and the M will percolate down into this, and I end up with JK, L promoted here, and M and O in this next one. And so long as I have enough space in the receiving one, I can pour more things. I could even pour the K would go up, then the L would go here, and I would have J, K, L, M, and O in here. I can do this redistribution as best suits me. So a combination of these operations is what we're going to use next time to show you how to implement deletion. I had spoken about deletion with the BST, but I had glossed over deletion with the 2, 3, 4 and red-black trees. And we are going to see the deletion in the BTrees. The BTrees were the thing that was invented before the same technique was ported back to memory for 2, 3, 4 trees, and then from there red-black trees. So once you explain it for the BTrees, which are the original data structure, then the rest will just follow. As you will recall, the motivation for BTrees was that we are dealing with a set of keys and satellite structure that is so large that it will not fit in the main memory. Nowadays it may seem strange to have anything that might not fit in main memory because main memory is so large. But even so, you can always come up with more data to throw at stuff. You know, large video file in 4K, 8K for that matter. There will always be something you cannot fit in main memory. And you may want to index the individual frames of this video, for example. So that's something where you have keys, values, and a precedent, an order among the keys, and you may want to retrieve individual keys with as close to random access as possible. So because what costs here is the disk accesses, you want to minimize the number of disk accesses. So pointer lookup, when your data is not in main memory, translates to disk accesses. And so to minimize the number of pointer lookups, you want the height of your tree to be short, because every time you need to go down another level in the tree, you need to do a pointer lookup from the parent to the child. So you make your tree as shallow as possible by making the branch out to a very large branching factor, which could be thousands. And you have this structure in the node where you have a minimum and a maximum number of children. Minimum number of children is called T. Maximum number of children is going to be twice that. And the only node that is allowed to have less than the minimum number of children is the root, because otherwise you could never have less than t items in the B tree. Every other node respects that, and in any case, the rules that are summarized up here together enforce the invariant that every path from the root to the leaf, which is where the keys and values are stored, most of the keys and values are stored, is going to be the same number of edges, which is going to be a very small number. With a branching factor of 1,000, this level has 1,000 nodes, this level already has 1,000,000 nodes, the next level has 1,000,000,000 nodes, and so on. Any branching factor could be higher. So what happens when you delete? Clearly, you will not be able to delete any value pair, key value pair from any of the middle nodes, because if you did so, then the two children that are on either side of the thing would lose their separator. So you're only going to be able to allowed to delete things from the bottom layer, where there are no children with keys and values. All the children of these nodes are just null things, like these little black squares that we had at the bottom of the red black trees. So it's all very well to delete something from the bottom only, except that sometimes the thing you need to delete may not be at the bottom. And also except that sometimes the node from which you want to delete something may already be at the minimum number of keys. And so if you deleted one more key from it, then it would violate the invariant that the node has to have at least t children. So last time I introduced 3 operations that are going to be useful for us to, in order to perform the deletion operation. And these operations were merging 2 nodes. Merging 2 nodes is something I am going to do, provided that I respect these invariants about the size. The node has to have at least t children and at most 2t children. So this translates to at least t minus 1 keys and at most 2t minus 1 keys. So the maximum size of a node is 2t minus 1 keys. The minimum size of a node is t minus 1 keys. And therefore, this merge is something that will only happen when I have t minus 1 keys in here, t minus 1 keys in here. If I add them up, this gives me 2t minus 2 keys. And because I have to merge them with 1 key coming down from the top, that's the one that separated them, then this in total gives me 2t minus 1, which is the maximum size. So I merge 2 nodes of the smallest possible size to obtain 1 node of the largest possible size. The split operation is the opposite, and for the same reasoning, can only be done on a node that is of maximum size, is already full of as many keys as it's allowed to have. And so I take a maximally full node and I split it in half, and the middle key goes up in the parent, and the 2 new nodes are created at the bottom layer, or at any other layer for that matter. In order to do that, I must be able to insert a new key in the parent. Just like in order to do the previous thing, I must be able to lose 1 key from the parent. If the parent itself already had t children and therefore t minus 1 keys, then losing this key would not be allowed. And so before doing that, I would need to somehow compensate, refill this node. So one way of allowing this is to do a merge with its neighbor, but I can only do that if the neighbor also has t minus 1 keys. If this one has t minus 1 keys, and I would like to drop 1 key down here, because otherwise it would have too few, but the neighbors don't have t minus 1 keys, means they have more, then what I can do instead is a redistribution of the keys between the nodes. So I can basically push things over in this direction through the middle key and there, so the middle key changes to being one of the donated ones from the adjacent richer sibling, and they are poured back into the node that had the minimum number of keys. I think I did an example with the actual letters last time. So these three operations together allow us to delete a node from anywhere. So if I'm deleting a node, which is a node, I'm now deleting a node, I'm deleting a key value pair. If I'm deleting a key that is already in the bottom layer and the node in which this key resides does not have the minimum number of keys, but more, then I just delete it and that's it, and I just go home because that's all I needed to do. This node is not concerned about the loss of one key if it's not the minimum number of keys, and nobody else is concerned either. If the node I want to delete a key from is in the bottom layer but already has just the minimum number of keys, then of course it's not allowed to delete a key from it, but I can use one of the strategies that I said. If either neighbor of this node, actually it's more complicated with this neighbor, if a neighbor of the node that is child of the same parent node exists with also t-1 keys, I can merge the two by dropping a key from the parent. But this may involve a recursion back into same operation for the level above in case the parent also had the minimum number of keys. And in that case I have to check, okay, does this also have a sibling in the same from the same parent node that has t-1 keys? Then I can merge it. But maybe I have to do it at next level up and so on. If the node does not have a sibling with t-1 keys, then I can do a redistribution because it must have then a sibling with more than t-1 keys. And it can donate some of these excess keys to my node that is otherwise going to have the minimum. And the same happens if I do it at another layer. So that sorts me out for deleting something from the bottom layer. What if I need to delete a key from anywhere other than the bottom layer? Well, if I am anywhere other than at the bottom layer, then to delete a key, I said I can't just remove it from here because it would cause trouble for the two adjacent children of it, the two children that are on either side of that key. I will use the same technique that we introduced when we spoke just of the plain unbalanced BST, which is to say, if I were to do an inversion between the node and its successor, I would upset the tree locally, but if I then delete the successor, then this upset goes away. So where is the successor of any node that is not in the bottom layer? I argue that the successor of any node not in the bottom layer is in the bottom layer. Because if you are not in the bottom layer, then you must have a right subtree. Because this tree is constructed in a balanced way. Every key anywhere other than in the bottom layer has a right subtree that contains something. In this right subtree, there's going to be a minimum value, and this minimum value is going to be the successor of the key we are talking about. So this minimum value is obtained by following the left pointer all the way down, and the left pointer will take me to the bottom layer where I will find my successor. So the successor of any node anywhere other than at the bottom layer is in the bottom layer, and I can just swap it for the node to be deleted and then delete it from the bottom layer with one of the techniques I already said. So that covers all the cases, and we are therefore able to delete a key from a node anywhere in the tree. And that same technique applies to the 2, 3, 4 trees, and with the appropriate translations, which we won't go into, also to the red and black trees. So here or somewhere else. Here is an example from your textbook of deletion. Not you, not you, you. And you as well. Okay, I hope I've done the right things. So here's a tree, a B tree with T. Looks to me like I should actually make a note of this before bringing it here, but looks like this is T equals 3, the minimum number of children, and therefore the maximum number of children is 6. And so the minimum number of keys is 2, and the maximum number of keys is 5. So in this tree, if I wanted to delete F, where is F? F is in a bottom node, and is in a bottom node that has 3 keys, and the minimum number is 2, so I can just delete it, and that's it. If I wanted to delete M, where's M? M is here. Is not in the bottom node, so I have to delete its successor. So I have to swap it with its successor and delete it in the place where the successor was a successor. If I look in here in its right subtree, and the minimum of the right subtree, that would be N. And so I have to swap the position of M and N, and then delete from there. So M migrates here, N migrates up here. But that does not seem to be what it does. Maybe he's swapping with the predecessor instead of the successor. The predecessor of M would be in its left subtree, would be the maximum of the left subtree, it's L. And so I bring L where M was, and I bring M down here, and then I delete M from here. That's what is done. So swapped with the predecessor. It's the same. If he then wants to delete G, that's where G is, he deletes G, and this is a case where if you use the same strategy of swapping with the predecessor, and the predecessor is E, but then E is 1, which is in a node that has already got the minimum number of keys. So if I swap G into here and E up here, then I'm not really allowed to delete the G from this node until I refill. But to refill, this has a minimum number of keys, this one also has, this one also has, so I can just merge it with one of its neighbors. And in this case, I merge it with this one over here. So in fact, you can see that this key would go down here if I merge it, and at that point I don't have to bother swapping the predecessor because the key that I needed to delete has now migrated to the bottom layer. And so I delete it, and I get this one, which now has 1 less than the maximum number of keys. And so on. What other cases is he showing us? If I then delete D, if I delete D, then I remain with this EJK. I think that what he's doing is he is using the dual of that heuristic that I introduced in the 2, 3, 4 trees on insertion, where I said I may not like getting to the bottom and finding I cannot insert there because it's already too full. And so to prevent that from happening, when I insert in a 2, 3, 4 tree, on the way down, anytime I find something that's already a 4 node, I will split it just on principle, even if it's not actually necessary for that case. I will just split it. It will be useful for later anyway. And then I'm guaranteed that whenever I need to insert, I can always push back. If I need to insert it to a 4 node, I can always split it and insert the key into the previous node, because that one will not be full, because I've already taken care of that on the way down. He's doing the dual of that for deletion. So for deletion, I may, if I end up deleting from a bottom node that already had the minimum number of keys, I may need to refill it and bring down something from the node above. But if the node above already had the minimum number of keys, then I have to keep doing that at higher levels. So this dual of the heuristic, as you by now understand, is that if I'm going to look for a node that I need to delete, as I encounter nodes on the path towards that node from the top that are already of minimum size, then I refill them on principle, even if I may not need it in this particular case. For example, in this particular case, just deleting D, I would not actually need to refill anything, because this node does not have the minimum number of keys. So it would be perfectly legitimate to delete D and leave this node as EJK. However, if I'm using this, this heuristic to save me trouble in case where I needed to bring a key down from above, then as I go here, P doesn't, the root doesn't count because it doesn't have a minimum, but this one is of minimum size, and so on my way down I decide to refill this one, and to refill this one I need to merge it with its sibling, and so I create a CLPTX node of maximum number of keys by bringing down the key here. But this one was the root, so this is the only case in which the height of the tree decreases, when I am bringing down the root into the bottom layer. But it decreases in a way that the length of all the paths in the tree decreases by 1 simultaneously. Just exactly the dual of what we had on insertion in a 2-3-4 tree. So here you can see all the paths to leaves now become 1 edge instead of 2. The root is now empty, and this becomes the new root. Tree shrinks in height. And then from that you delete B. Okay, well, deleting B in this case is one where I cannot merge this node of minimum number of keys with its neighbor, because this one is not minimum number of keys. But what I can do is a transfusion, what I call a refill, and so I can lend this E key going up here, and this one acquires the C key, the E key becomes the separator, and then this node that now has ABC, I can drop the B from this one and becomes AC. The E has moved to here, and then I have JK, which is the rest of this one. So this is all the things you can do with deletion from a B tree.